the presentation for the coursework of good deep learning. Um, our topic for presentation today is rethinking few short image classification. A good embedding is all you need. Next, this is the content includes objective, introduction, paper contribution, method, result, and summary. In this paper, they propose an extremely simple baseline that suggests that good learned representation are more powerful for few short classification tasks than the current crop of complicated meta testing algorithm. It is a simple baseline learning a supervised or a self-supervised representation on the meta training set, followed by training a linear classifier on top of this representation outperforms state-of-the-art few sort learning method. An additional boost can be achieved using self-distillation. This demonstrates that using a good learner embedding model can be more effective than the sophisticated meta-learning algorithm. This finding motivates a rethinking of a few set image classification benchmark and the associated role of the meta-learning algorithm. Meta-learning algorithm. Meta-learning defines a family of tasks divided into disjoint meta-training and the meta-testing sets. This is a challenge that only limited data is available to adopt the model. The problem arises the concept of meta-learning. The goal is to learn to learn. It is used to improve the results and performance of the learning algorithm. It basically reduces the dependency of the allowing deep neural network to learn new concept quickly. It is widely used in the area of few short image classification. Next.
So few-shot learning means making classification or regression based on very small number of samples. So it is different from the standard supervised learning. So the goal of few-shot learning is not to let a model recognize the images in the training set and then generalize to test set. Instead, the goal is to learn. So in this, first we train the model on a big training set. Then the goal here is not to learn, to classify to a specific class in training set, but the goal is to learn similarity and differences between objects. So model learns a general representation, that is similarity and differences between objects. So now given a small train set, which is also called a support set, which can have unseen class objects, this model can identify also unseen objects, which were not present in the big training set. So the main difference from the traditional supervised learning is that in traditional supervised learning, test samples are never seen before, but test samples are from a known class. But in few-shot learning, the test samples are from an unknown class, and we can classify them using a small support set. So the paper contributions. So this paper basically shows that meta learning doesn't work for few-shot classifications. So this paper suggests that good learned representations are more powerful for few-shot classification tasks than the current crop of complicated meta-learning algorithms. So this baseline suggests that many recent meta-learning algorithms are no better than simply learning a good representations. Also, building upon this simple baseline, if we use the self-distillation, it can further improve the performance. So combined method achieves an average of 3% improvement over the previous state of the art on widely used benchmarks. Also on the new benchmark metadata set, this method outperforms previous best results by more than 7% on average.
In this paper, they establish various methods about the meta-learning problem and the related algorithm about the baseline model. Then how knowledge distillation helps in the few-shot learning. Like a base learner is trained on D-train and used as a predictor, D-test for the high dimensity, the base learner suffers high variance. So the training example or testing example are mapped into the features space by an embedded model. The objective of the meta learning algorithm is to learn a good embedding model so that average test error of the base learner on the distribution task should be minimized. So the goal of the meta training is to learn a transferable embedding model, which generalized to any new task, rather than designing the new meta learning algorithm to learn the pre-trained on a classification task can generate powerful embedding for the downstream learner. In this task, basically, merge tasks from the meta training set into a single task. Next. In this figure, it is shown that basically the meta training, they train an image classification task on the merge meta training data to learn a embedding model. This model is then reused at meta testing time to extract embedding for the simple linear classification. Next.
So their baseline consists of a linear model learned on the top of a pre-trained embedding. So this outperforms all the other meta-learning algorithms on few short classification tasks by large margins. They have not utilized information from testing data and have used a fixed neural network for feature extraction rather than fine-tuning it on a meta-testing stage. So this model learns representations by training a neural network on the entire meta-training set. That is, they merged all the meta-training data into a single task, and then a neural network is asked to perform ordinary classification on this combined data set. And then after training, they have kept the pre-trained network up to the penultimate layer and use it as a feature extractor. So that during meta testing stage for each task, they have fit a linear classifier on features extracted by pre-trained network. Further self-distillation on this baseline provides an additional boost. So self-distillation basically means we trained a larger single model, a small model to match the output of a larger single model. Doing so, we can get a boost in the test accuracy. So as we can see in the figure, in the support set, we have 5 images, and in the query set, we have 1 image. So this is the 5-way one-shot task. So the task is here to match the find the most similar image to the query image in the support set. So these 5 support images and 1 query image are transformed into embeddings using the fixed neural network. Then a linear model is trained on these 5 support embeddings. Then the query image is tested using the linear model.
So you said the query image is tested using a linear model. That means a cosine similarity, or what sort of similarity? So you get 5 embedded representations for the 5 support set images, right? So 5 vectors, so to say, and 5 vectors for the 1 vector for the query. So how do you get the similarity?
Sir, actually, they have also used the cosine similarity as well as the nearest neighbor, sir. Both.
And do they show anything that okay, this one is better, like cosine similarity or nearest neighbor? Which one is better? Which one is giving better results?
So they have also used the. Sir, they have said that nearest neighbor usually performs well.
Okay, go ahead.
Results. During meta testing, the evaluation is done for method with 3 runs, wherein each run the accuracy is the mean accuracy of the 1000 randomly sampled task. Their simple baseline with RexNet 12 is already comparable with the state-of-the-art MetaOptNet on Mini ImageNet and outperforms all previous work by at least 3% of the TiredNet ImageNet. The network trained with distillation further improves over the simple baseline by 2 to 3%. Basically, the RexNet 12 is basically pre-trained before mining hard tasks for the meta training stage. In this work, they showed a standard cross entropy pre-training is sufficient to generate the strongest embedding without meta training technique or any fine tuning. Next.
So you have your 10 minutes are up, but you can take like one more minute to wrap up.
Okay, sir. Okay. Similar to the previous result, they evaluate the method with 3 runs, where in each run the accuracy is the mean accuracy of 3000 randomly sampled tasks, which shows that our simple baseline is comparable to prototyping network in MetaOptNet on CipherFS dataset, and the outperformed both of them on FC100 dataset. This distillation version achieved the new state of art on the board dataset.
So in summary, this paper basically shows that meta-learning doesn't work for the few-shot classification. This also shows that representations play an important role. As it is shown by various empirical experiments, a linear model can generalize well as long as a good representation of the data is given. So also with various numerous experiments, a simple baseline outperforms the current state of the arts on 4 widely used few-shot benchmarks. Also combined with the self-distillation, the performance further improves by 2 to 3%. Thank you.
Okay, one or two comments rather, not questions. So your slides have become a bit text heavy. So since this is a computer vision paper, try to give images. I mean, text heavy does not appeal people, okay, as audience.
Yes, sir. Yes.
Now, another thing is that there was a paper I remember in CVPR 2019, meta transfer learning. So do they compare with that? Because they showed, if I remember it right, that they also did a baseline with like combining all the meta training data as a single data, then training it sort of the base network, then freezing it, just use it as a feature extractor, and they showed that okay, that was not working as good as the meta training. But did this paper compare with that meta transfer learning? Just try to see. You might not remember now, but try to see if
yes,
they compared with meta transfer learning. Okay. Thanks. If there is any quick question from anybody. Okay. So thanks again. I'll go to the next.
Thank you, sir. Thank you, sir.
Yeah. So the next team is team 18 and Krinal and Sarvesh. So you are there?
Yes, sir.
Yeah. So can you try to share your screen?
Yes.
Yeah. Your
Is my
time
screen
will
visible?
be, yeah. Your time will be 10 minutes. So you can divide among yourselves who will present which
Okay.
part. Yeah, you can start.
Just one second.
You should keep it ready. Why are you doing it now?
Sorry, sir.
Yeah.
Sorry for the delay.
Already your 1 minute is gone. So keep that in mind. Yeah.
Hello everyone. Today we are going to discuss an interesting paper on born again neural network. So in this paper, authors have used knowledge distillation to reduce generalization error of a model. So first I will introduce knowledge distillation and later we will move to born again networks. So first of all, what is knowledge distillation? So it is a transferring of knowledge from one machine learning model, which we typically call teacher, to another machine learning model, which we call student. So in the typical setup of the knowledge distillation, teacher is a high capacity model, so which has very really good performance, and a student is a much more compact model. So normally we use knowledge distillation to compress the model. So we get benefit from the student's compactness without sacrificing too much performance. However, in this paper, authors have not used knowledge distillation for model compression purpose. Rather than compressing the models, they have trained students parameterized identical to their teachers. So basically, they have take students having the same capacity as their teachers. So what is the born again network? So it is a simple retraining procedure. So once the teacher model converges, we initialize a new student and train it with the dual goal in mind. One is predict the correct level, and second is matching the output distribution of the teacher. These students are called born again networks. And they authors have found that this BN outperform the teachers significantly on the computer vision as well as language modeling tasks. So this is a graphical representation of the BAN training procedure. In the step 0, they have trained teacher model using the ground truth labels. And in the subsequent steps, they have taken student with the different random seeds and train under the supervision of the previous generation. So, for example, in the K step, the student is SK and the previous generation was a K minus 1. And they have also taken multiple generation of the students to create an ensemble. So before going forward, I would like to introduce another term, which is dark knowledge, which will be required later. So in the first diagram, we can see that it is a one-hot encoding of the output. And in the second, it is a probability distribution of the logits. So the first only says that this image is a dog, which doesn't reveal any other information. However, in the second image, it consists of probability, so which contain very useful information. For example, we can say that this image is less likely to be classified as cow, but it also says that it is even lesser chance that this image will be classified as car. So dark knowledge can be defined as the knowledge which is hidden in the distribution of logits of the wrong output, which carry information on the similarity between output categories. And BAN used this dark knowledge to improve the performance. Okay, so on the previous papers on the knowledge distillation have shown that the generalization error can be reduced by modifying the loss function. So how it is done in the born-again networks? So the answer is dark knowledge. Born-again networks exploit the idea demonstrated in the knowledge distillation, that the information contained in a teacher's output distribution can provide a rich source of training information, which leads to a second solution with a better generalization. So we can see the loss function here, and which is basically cross entropy between the new model's output and output of the original model. Now Saris will continue.
Yeah, so moving ahead, we are discussing the following cases that can be obtained by some manipulation in the Venn model. So the first one is sequence of teaching self. Psychologically, it is said that the process of human learning is like teaching oneself sequentially. Inspired from this perspective, the author of the paper utilized the DenseNet to perform knowledge transfer sequentially. The KH model is trained with the knowledge transferred from K-1 student or model. So the loss function will turn out to be this. And the fitting function will be shown below. The fitting function is simply an average of all the Venn models, all the K-Venn models. So moving ahead.
What did you say? This is fitting function.
Yeah.
And this is used during inference, right? I mean, this f hat k. This is never used during training, right?
Sir, it is finally computed after complete computation of all the K generations.
Yeah. So it is. I mean, my question is that I got, but my question is it only used during inference, or is it used somewhere in the training also?
Sir, we can see that it can also be used in loss function, but
yeah, but it can be. Yeah. But did they use? That's what my question.
It is not mentioned there that they used, but
okay.
Yeah,
so be confident that they did not mention anything about that they did use it.
Yeah, but okay. It can okay. Yeah. So moving ahead. Yeah. So the success of dark knowledge. So it can basically depend on dark knowledge hidden in the distribution of logits of the wrong responses that carry information on the similarity between output categories. Like we can see that there is similarity between cat and dog, but it is not similar to car and the other one. So we can get this knowledge from this. And another valid explanation might be found by comparing the gradient flowing through output node corresponding to the correct class during distillation versus normal supervised training. So the gradient of the cross entropy loss between student logits and teacher logits is shown here. In this, the first term corresponds to the gradient of the correct choice, whereas second term corresponds to the information incoming from the wrong output, that is through dark knowledge. Moving ahead, So this information links that there might be an importance of weighting. So now the two questions arise in our mind that does the success of dark knowledge owe the information contained in non-argmax output of the teacher, or is the dark knowledge simply performing a kind of importance weighting? So for these, to answer these questions, we develop two treatments. One is confidence weighted by teacher mix, that is CWTM. So basically in this, we don't consider the effect of dark knowledge. We weight each example in the student's loss function by the confidence of teacher's model on that example. And the second is dark knowledge with permuted prediction. So here we basically permute the non-argmax output of teacher's predicted distribution. So moving on. So in this experiment, basically, we are comparing all the possible models that can be generated as on the discussion we had before. So these are all the terms used in the experiment. So we are using DenseNet of different depth and growth factor, whereas we are using Ben. Ben is a model trained just using teacher's loss, whereas Ben plus L models is the model trained using both label as well as teacher loss. CWTM is as discussed above. DKPP is also the same. And sequence of Ben, DenseNet and Ben ensemble resulting from the sequence that we have discussed before. So these are the labels we are using ahead. So moving on. So this is the output of the test we conducted on the Cypher 100 dataset. So in this we can say that comparing different model based on the test error they generated, DKPP has less test error as compared to CWTM for lower depth and higher growth factor. Otherwise, both have similar test error. These results demonstrate that knowledge distribution does not simply contribute information of one specific non-correct output. Whereas moving on towards Ben models trained only with teacher loss has lower test error than Ben models trained with both label and teacher's loss. And going ahead, Ben ensemble models are performing better for all the models, and the more number of models are ensembled, lower is the test error. So moving ahead, finally we can conclude that the biggest contribution of this paper is that transfer learning between models with similar structure as possible through knowledge distillation, and it can be seen that all the Ben network outperform the teacher's network. And these are the results we discussed before. So thank you.
Okay, thanks a lot. It was good presentation. I see that you have also mentioned about the sources of the images that you have taken. That is a good practice. Another thing is just a small question about the DKPP. You said that it permutes the non-correct or permutes the logics of the corresponding to the non-correct output, right? I mean, non-correct classes.
Yeah.
So basically, so they just permute the values, right? So for example, say you are classifying a 10 class data set, right? So there are 10 classes. Suppose for a particular example, say the second class is correct one. So excluding the second class, that is the first class, and then third, fourth, fifth, these are just jumbled up, the outputs. They are
just jumbling the output of they are just jumbling the wrong output.
And you are saying that DKPP is performing better than CW?
Yeah.
That's a surprising thing. I mean,
no, sir. Okay. In this, we are removing the.
Actually, sir, it is not surprising. So in the CWTM, they completely remove the dark knowledge.
Yeah,
they are permuting.
Yeah,
in
but
dark knowledge is remaining there.
Yeah, so one is removing the dark knowledge, another is like supplying with a wrong dark knowledge. I mean, the
Yes,
DKBB is sort of wrong dark knowledge. So that's why it was becoming.
Uh-huh.
I mean, sometimes it may be better to give no information than giving wrong information. That's
From that point of view, you're right.
yeah.
Yeah.
Yes.
It's surprising. Okay. Anyway, it was good.
Sorry
so
for the
yeah.
inconvenience in the
No, that is fine. Yeah, I didn't deduct marks for that. No problem. Anyway, okay. So if there is any other questions from anybody, quickly. Okay. Thanks again. I think there is no question. So you can
Yeah,
unshare yours.
Yeah,
I can
okay.
go
Thank you, sir.
open, next team, which is team 19. So Shubhranil and Aryan. So you can share your screen. Yeah, I can see your screen. It's not slideshow mode though. If you want to go to slideshow mode, you can go ahead. Yeah, but slideshow is, I am just seeing the desktop. So maybe you have not shared the whole screen. You might need to share the whole screen then.
Is it now not visible? Okay.
I mean, I'm seeing the
slideshow
I'm seeing
start कर दे.
yeah, but then but still I'm see
Okay,
when you
okay,
are
I'm
starting
just-
Share the whole screen, yeah.
you have not shared.
Yeah, I've shared the whole screen only. I'm resharing this just